time for us to get started. We are on our last section, which is Stokes' theorem. There are a couple of versions of Stokes' theorem we're going to deal with. Essentially, today is going to be the first version. I'm calling it version 1. And it allows us to find this surface integral. So, surface integral of the curl of f ds. So if you get a question that says find this, then what you do is you convert it into a line integral. And the line integral f dr, where f is, you know, your typical vector field, and the surface is converted into a three-dimensional curve C, and that three-dimensional curve C is going to be described by r of t. So I'll try and draw a very bad example. Can you imagine this is a surface? So it goes up and in and so on, but on the boundary of the surface, you've got your r of t. And so that's what C is. So we are going to be looking at converting this double surface integral with the curl into a single line integral using a closed loop C. And we're going to solve this by converting the thing into a parametric equation using t.
So we're converting it. It looks like we're converting it from a double integral to a single integral.
Yep, and that single integral is going to be converted into t, where t is the parameter that we'd used in the intersection of this surface. So, I just got plain piece of paper. It drives me crazy to try and draw it any other way. But essentially, you're going to have a surface, and this surface has an outside boundary, and that outside boundary is who C is, right? So maybe can you imagine the surface look like this, right? That's the entire surface, right? Doesn't that surface have a boundary, right? An edge to it. So that's C, and this is S. Does that make sense, what I'm saying, right? So you got a surface, but the surface has a finish, right? It has an end, an edge. And the curve that makes the edge of it is going to be that C. So we're going to figure out who that fella is in terms of r of t. We are then going to plug it into here. So all of these get converted into functions of t, right? Dot product with the derivative of the space curve, dt. Well, let's jump right in and just show you one. I think that's going to be the easiest way to do these. Have I got questions set up? No, I haven't. Okay. Give me a second to click on. Okay, we got one. So in this particular question, I'm going to start with question 3. We have got a vector field F, which happens to be x squared sine z, y squared xy. So we're given that fella, right? The surface S is described as a paraboloid, which is that guy, that lies above the xy plane. So that's basically just means z equals 0. So we are trying to create, or trying to find at least, this fella. So this is a surface integral that we're being asked to find. Now, I'm not quite sure why anybody wants to know this surface integral, and it's probably got a name, and I don't know what its name is. But you know, like remember the other one that had a name, which was called the flux? This has probably got a name, and so they probably want to know it for whatever reason. So how are we going to find this guy? Well, we know the vector field, that's good. We know the surface S is a paraboloid, so it's probably one of these guys, right? And then it meets the XY plane, which is the floor. So I need to find out essentially R of T. So first thing I'm going to do is find R of T. R of T is the parametric equation of the boundary curve. See, well, what do I know about it? I know it's this guy, and I know it meets up with the floor. So basically, the floor is Z equals 0. And if you make Z equals 0 here, so you've got Z equals 0, that's one of your parameters. If you make Z equals 0 here, can you see that we end up with that? If you rearrange this, you get that. Are we good so far? So basically, isn't this just a circle on the floor? So if you imagine what it would look like in the 3D world, our C is actually just a circle on the floor. And we have to find the parametric equation of that. And it's a parametric equation, a space curve, right, from Calc 3. So it's got 3 components. So here goes. Not doing it yet, 0. Would you agree that that space curve, the Z component is going to be 0 because it's on the floor? Right. How would you generate, oops, there's a plus there. How would you generate the equation of a circle in a parametric form? Well, the X coordinate would be 3 cosine T, and the Y coordinate would be 3 sine T. Are you comfortable with the parametric equation of a circle radius 3? You're not comfortable, are you? Would you agree that that would give you this? Right. So that is the creation of the parametric curve. So far, so good. So you've got this to find. The first thing we need to do is get the parametric equation of the boundary C. So this thing here is a big, paraboloid thing up here, right? That's the surface. But when it hits the floor, it makes a curve, right? That's the edge of it, the boundary. Next thing we're going to do is we're going to find the derivative of this guy, which is -3 sine T, cosine T, 0. And now we're going to use this formula here. So, oh, by the way, if it's going to be a circle, isn't T going to go from 0 to 2 pi? Right, I want once around the circle. Right. So, I wish I had more pieces of paper. Third thing we're going to do, I'll just write it down here again. We've got this guy, the thing we're being asked to calculate. And it's going to become this fellow. So it's going to be from T equals 0 to T equals 2 pi. The vector function evaluated at RT, and RT is this guy. So we're going to do that thing. Dot product, this guy. So the only thing that's missing is, what does this look like? Right, well, if you write down the original value of f, it's up here, it's x squared sine z, y squared xy. If you use R of t, which was 3 cosine t, 3 sine t 0. And you use that to be the x, that to be the y, and that to be the z, then this guy will turn into...
Excuse me,
Yes.
on r prime of t, why is it not 3 cosine t?
It is. I just missed it. Right. So this guy is x squared sine t. So this guy squared, the sine of z, which is 0, comma, y squared, which is just 3 sine t squared, and xy is going to be 3 cosine t times 3 sine t. So I'll now convert this guy into, well, it doesn't matter because that's 0. That's going to be 9 sine squared t, and that's going to be 9 sine t times cosine t. So I've got my f now in terms of t. I've got my r dashed guy, just to rewrite him again. The formula says that it is basically, it's a dot product of these. So it's going to be the integral from t equals 0 to t equals pi. This fella. This fella. Okay, not enough room. Maybe I should write smaller. dt. So when you take the dot product of the vector function expressed in t times the derivative function expressed in t, integrate with respect to t, you will get from 0 to pi. Nothing times that is nothing. 9 times that gets me 27 sine cubed t, and that times that gets me nothing. So the original integral ends up being the integral of this fella, which is from 0 to pi of, plug the 27 outside of that guy. So now we need to figure out how to integrate sine cubed. Any suggestions from Calc 2 how to integrate sine cubed?
Why is it sine cube? Shouldn't it be sine squared t cosine t?
Let's check. That guy times that guy. 27 sine cubed.
I think you got them switched
Oh,
up.
did I? Which
Yeah.
law? Who's
Because-
switched out where?
Wait a minute. Oh, never mind.
Am I good?
Uh,
That guy's
Actually,
F
no.
and that guy's RT.
Wait, I am so confused. Okay. No, yeah, because we had the original R of t was 3 cosine t, 3 sine t, 0. The derivative of
Oh,
3
is
sine t
that,
is
did
3
I
cosine t.
transfer it wrong? I did.
Yeah,
didn't
I think you put over the original R of t instead of R prime of t.
Oh, shooting space. Sorry about that. Okay. So pretend that never happened. We have this fella, which ends up being 0, 9 sine squared t, 9 sine t cosine t. We have this guy, which is one I should have got, and that guy is -3 sine t, 3 cosine t, 0. And so the surface integral for the curl of f ds is going to be the integral from 0 to pi of f dot product r dash t dt.
Is it 0 to pi or 0 to 2 pi?
2 pi. That times that guy is 0. That guy times that guy is now 27. And I think we have a sine, cosine, cosine, don't we? So we're going to get 27 sine t cos square t. That's where the problem happened. And that times that gets
No, because those two terms go to 0, the last two terms go to 0. And so then you have 9 sine squared t times 3 cosine t.
There we go. So we get 27 sine squared cos squared t is 0. I'm going to have to write 0 because this scanning is killing me. And at this point, the hard part eventually is over. I'm going to do 2 more of these, so hopefully I'll get them right by the second time. But how are we going to integrate that guy anyway?
It would be u sub and spoiler alert, since you used the sign for the u sub, then that would make it a 0. Oh, and
Okay.
Terrence has a
Hi,
question.
Terrence. Yeah, Terrence, what's your question?
Sorry, it got answered and I forgot to put my hand down.
Okay, then that's good. Right. So basically, you'll do that, and the answer is whatever it happens to be. I don't have a copy of that one handy. Right. So a kind of hit list of what we're going to do. I'll keep that my little hit list. First thing I'm going to do in the next question is find out who R of t is, right? That's the curve C, and it's the boundary of the surface S. Second thing I'm going to do is I'm going to take F and I'm going to convert it into T's. Then I'm going to take the dot product of those two guys and we'll be finished. So that's the main basic strategy for doing this. So next fella, got one over here set up. It's going to be 4. So we have 2y cosine z, e to the x sine z, and x e to the y. God, these things are just big. S is described as a hemisphere. That's half a sphere. And it's a hemisphere, x squared plus y squared plus z squared equals 49. And it's with the floor again. So if you can imagine what that surface would look like, it's a hemisphere, right? Half a sphere, and it's in z equals 0. So it's basically this guy here, right? The top half of a sphere. Are we good? Right, now, the boundary, the R of t, is where the edge of the surface is, right? Where the surface hits the floor. So we are pretty much doing, in 3D again, almost a carbon copy of the last question. Isn't the C shape a circle on the floor? Right. So the boundary of that surface is the circle on the floor. That's C. And since it's on the floor, Z equals 0. And since if you make Z equals 0, can you see that the circle on the floor has a radius of 7? And so that is going to be X equals 7 cos t and Y equals 7 sine t, and it's a whole circle. So that's going to be from 0 to 2 pi. Are we comfortable about the parametric equation of this circle on the floor? Because when you put that together, you will get a 7 cos t, a 7 sin t, and a 0. So far, so good. Now, that's number 1 done. Parametric equation of the boundary curve C. Now we're going to convert this vector field into t's, using that for the x, that for the y, and that guy for the z. So the vector field f is going to be 2, the value of y, times the cosine of z, which is 0, comma. E to the x, which is going to be that guy, times the sine of z, which is sine 0, and 7 cosine of t, e to the 7 sine t. Are we comfortable that I did that right? X, y, and z transferred. Now, make it look pretty, or at least as pretty as we can. Cosine of 0 is 1, and 2 times 7 gets me 14. So that's 14 sine t. Isn't the sine of 0 0? So that term is just going to be a 0. And this guy at the end is going to be 7 cosine t, e to the sine, 7 sine t. Are we comfortable about the simplification of f, the tidying up?
Where did the -1 go?
What -1? Do you have a -1 somewhere?
Am I reading about further that thought you oh, multiplied by cosine of 0, never mind.
Sometimes my dots become more minusy sign than they should. Right. Now, we know the formula for the surface area, this one. Stokes' theorem says if you want to find this guy, you find a line integral, and it's going to go from t equals 0 to t equals 2 pi, and it's going to be the dot product of f derivative of t dt. So it's going to be the integral from 0 to 2 pi. We already know who f is. It's 14 sine t, a 0, 7 cosine t. Dot product, get it right this time, the derivative of this guy. And differentiate that, you get negative 7 sine t. Differentiating that, you get positive 7 cosine t, and differentiating 0 gets me 0 dt. So it's going to be the integral from 0 to 2 pi. This guy times this guy is going to be negative 98 sine squared. This guy times nothing gets me nothing. This guy times that guy gets me nothing dt. And so I now have the integral from 0 to 2 pi. I'm just going to pull out that negative 98 and leave us with a sine squared. So it didn't actually end up too ugly at the end. You agree? Now, in the previous question, it would be a u sub. That's not going to work here. So how are we going to integrate sine squared t from Calc 2?
A trig identity.
Okay, and the one that we're going to use is the one that is a half. 1 take away the cosine of 2t. So I might as well suck out that half and find the integral from 0 to 2 pi of 1 take away the cosine of 2t. And I think at this point, I could do dot, dot, dot. I think that one went a lot smoother, right? I think if you organize things as I did with the second one, it just keeps the process under control. Now, there's one little hiccup. There is a positive and a negative orientation going on here. You know how you can go around a curve positive or you can go around a curve negative. And so the answer you might get might be positive or negative. So if the one you've got doesn't match, well, you just put in the other one with a negative. It just, the orientation was going the other way, right? So if you get 4 and it says it's wrong, just put in -4 and you'll be okay. As long as everything else is the same. And if you do -4, then try the other one 4. So orientation is an issue. If it's positive orientated, shouldn't the answer be plus? Well, if it's positive orientated, shouldn't you not change the answer? Let's say that, right? And if it's negative orientation, shouldn't you stick a minus in front of it, and it turns into what it turns into? So positive orientation, whatever the answer you get is correct. If it's a negative orientation, you have to, stick an extra negative and switch it around. You feel a little bit more comfortable about the second one than perhaps the first one, right? Can I move on to the next one?
This is certainly explaining some of the weirder stuff you can see in video game engines.
It does. Well, I have no experience of that, so that's kind of interesting. Where am I
Well,
off to
you
next?
mess up one dot product when you're attempting to model physics in a game engine, and all of a sudden you're launching, people into orbit when you kick them.
Oh, so it's to do the dynamics of movement. Okay, I gotcha. I think I just did this one, did I? It looks like that might be question 4. It is, right? I've done that one. That was my notes for it. We've got one more left, yes. This one. Oh, I'll just hide it for a minute. Question 3. Vector field is this guy. And our surface is another one of those paraboloids.
Didn't we do this guy earlier?
Did I? Oh, you're right. You did. So it's number 2. And this particular one, they all kind of start looking the same after a while. So this one is z e to the y, x cosine y, and x z sine y. And S is a hemisphere. That's good. So it's x squared plus y squared plus z squared equals 25. It's only half of the sphere. But here's the tricky part. It goes that way. So here's my x, here's my y, here's my z. If you make y equal 0, you're going to get a circle that kind of comes out this way. A circle. I can't draw spheres to save myself, but it's hard to draw a sphere in 2D anyway. If I orientate it slightly differently, there. Can you imagine that's that guy? And this here is the XZ plane. So what we're looking at is, yes, it's another circle, but that circle is in the YZ plane. Not the YZ plane. The XZ plane, right? It's in this wall here. Parametric equation. Y is 0. So something, 0, something. It's still a circle. And the circle is x squared plus z squared is 25. So that's going to get me a 5 cosine t and a 5 sine t. Are you comfortable with that? So this one's not on the floor. The boundary is actually, try it again. The boundary is on the XZ wall, right? So it's on that side. right? And that's the parametric equation. If it's a circle, can't you just do 5 cosine, 5 sine, and put 0 in the middle? So we have got step 1. Find the parametric equation of the boundary curve C. So it ends up being this guy here. My vector function, my vector field is this fellow. X is that guy, Y is 0, Z is that guy. So my vector function ends up being 5 sine t times e to the 0, 5 cosine t times cosine of 0, plus 5 cosine t, 5 sine t, sine of 0. Let's see if I can simplify that down. E to the 0 is 1, so that becomes 5 sine t. Cosine of 0 is 1, so that becomes 5 cosine t. And that times nothing just gets me nothing. So here is my f. My derivative guy is going to be negative 5 sine t, 0, 5 cosine of t. So ready, go. The surface integral of that guy is going to be the integral from 0 to 2 pi of f dot product derivative of the curve dt. This guy times this guy, I believe, is negative 25 sine squared t. This guy times this guy is nothing, and this guy times this guy is nothing. So we're looking at that. I would probably pull out the negative 25. And essentially, we only end up with integrating the sine squared. So find the space curve for r of t, right? That's the boundary of the surface. Use the values of this for x, y, and z. Plug them into here, here, and here. Simplify it out. And now you have the vector field using t. You've got the derivative using t. The dot product of these gives you the thing that you're going to integrate. And that's you got your integral of your curl. Any problems? We good? I mean, they are 3D-ish, which they are. Trying to figure out the boundary curve looks like it's an issue, but it looks to me like they make them all circles, I guess, to make your life easy, right? Because if the boundary curve was some weird thing, it would be very difficult to get the equation of it. So I guess that's why circles are the go-to shape. That is the end of version 1 of Stokes' theorem. That's the name we give to this method that allows us to find this particular surface integral.
Man, I'm so stoked to do this.
Oh, you were waiting ages to say that, weren't you? Tessa, should we bar him from telling jokes for the next 5 minutes?
No, keep them coming, Tim.
Okay, you've definitely got a fan there.
It's just a lot of work.
Excuse me a minute. I'm looking for another set of notes. Oh, here we go. Stokes' theorem has two versions. The one that we've just used allows you to get this surface integral. And you convert it into a guy that looks something like this. Now, the other version of Stokes' theorem essentially says you can change a line integral into a double integral. And do you recognize this ugly thing in the middle is just what the curl of f is? I'm just writing down its formula, right? So the curl of the vector field f is this, right? And you can take this guy and you can turn it into a d, right? So a curve, and it has to be a closed curve, right? It has to start and finish at the same point, right? So can you imagine that the curve could be that guy? Then won't d be the inside of it? Does that make sense? So C is that guy, and D is the 2D region inside. So it says you can take a line integral and make it into a double integral. D is a two-dimensional surface formed by projecting S onto the XY plane. So you might have a surface up the top here, but when you hit it on the floor, it turns into this guy. So that's how we get it into a two-variable world. And that's obviously what the curl of f is. So let's find our first example of that. Well, question 5 is a video that you can watch and do. The real beginning of questions with us. Good grief. Get the time. Anyway, let's at least see if we can do this one. We are being asked to find that line integral, right? And we're told that f is x plus y squared, comma, y plus z squared, comma, z plus x squared. And we're told, what else are we told? Oh, we're told that C is a triangle and it's formed by the points 7, 0, 0 to 0, 7, 0 to the point 0, 0, 7. Now these are three-dimensional triangles. So you can imagine the triangle might look like that in 3D. But what we need to do is we need to take that guy and essentially you drop him onto the floor. And you will get this guy. So this is D and this is S, right? So you start off with a surface and you drop it, you know, you basically do its shadow on the floor. So let me take these 3 points, 7, 0, 0, 0, 7, 0, and 0, 0, 7, and figure out what they would look like when they hit the floor. When you hit the floor, doesn't the Z coordinate become 0? So this guy will become 7, 0. This guy will become 0, 7. And this guy will become 0, 0. Are you happy about how I found the X and Y coordinates of these 3 floating points, what they would look like when they hit the floor? Well, let's see visually what we have here. We have an origin, a 7, 0, and a 0, 7. So this is the region D. So I've got enough room. I think I can do it here. For region D then, won't the X's go from 0 to 7? I don't know how many triangles we've done, but it seems we've done an awful lot of them. And won't the Y values, they will go from 0 to that straight line. And that straight line has equation 7 minus x. Are you comfortable with the equation of the line? Right. Slope of -1 has got a 7. So I'm beginning to have all the pieces I need. To find this guy, I need to find a double integral where the x goes from 0 to 7 and where the y goes from 0 to 7 take away x. According to Stokes' theorem, the guy in here is going to be the curl, and it's going to be a dy dx. And what do we get? We get negative p, I'll just write it down, negative p this guy, negative q this guy, plus r. So it's going to be the integral from 0 to 7, y equals 0 to 7 take away x. Where is my space curve? Here it is. It's the negative of x plus y squared times this guy. I told you who he is yet. Take away y plus z squared times this guy plus this guy dy dx. And we have a problem. I don't have a z and I don't have a g. Well, actually z is g. So I need to find out what the function that we're dealing with is. So if you go back to the original question, which is this one, the plane, this fellow up here, this triangle, right? It's basically the plane. That's the equation. That's the guy that's going to be called z is equals g of xy. Now, if you go and you find the equation of the plane joining these 3 points, well, actually, can anyone tell me, just looking, what the equation of the plane that joins these 3 points? And don't overthink it. Passes through this point, and this point. In 3 dimensions, what's the equation of the plane that passes through these 3 points?
Am I oversimplifying it and thinking that it'd be x plus y plus z equals 7?
You are not. That's exactly what it is. Otherwise, you'll have to do a whole load of work to find it. Now, if you rearrange that, doesn't it now become 7 take away x take away y? So when you're asked to find dg by dx, don't you just differentiate this with respect to x, which is -1? You want dg by dy, you differentiate this with respect to y, which is also -1. And if you want z plus x squared, don't you just replace this guy here? So you're now going to have, instead of that fella, you're going to have a 7 take away x take away y. Here goes. It's the integral from 0 to 2 is the integral from 0 to 7 take away x. -1 times that guy basically just gets you x plus y squared. -1 times that.
Oh, why does x go from 0 to 2?
0 to 7. I can't read my own writing. Right. That guy gets you that fella. This fella gets you 7 take away x take away y plus x squared dy dx. Almost done.
Oh, and it's -1 because of z equals 7
Derivative.
minus x
Yeah.
minus 1.
So differentiate that with x, you get -1. Differentiate with y, you get -1. So that's these two guys are. It's g. What do I get? 10 and I can collect here? Probably not much. I have an x squared.
You have to
your,
plug in.
and your x's would cancel out, and just your y's would cancel out.
They do. You can
Well,
see
you have
that.
a positive y, and then you have the negatives from the 7 minus x minus y.
Oh, that cancels with that. That cancels with that.
Yeah.
You have to plug
I
in
gotcha.
for that other z squared.
Yeah, and I forgot to plug in this guy, didn't I? Because everything has to be in x's and y's. Okay, 0, 7, 0, 7 minus x. X squared plus an x squared gets you 2x squared. Y squared plus a y squared gets you 2y squared. You're going to get negative 14 x's. You're going to get negative 14 y's. And you get negative 14. Oh, two negatives make a plus. Yeah, you're going to get plus 14 xy's plus 7. And can you just trust me that that may be right? Because I don't have enough time to foil it out and make sure that I've done it right. But if you foil that all out, you probably get the stamp. And that's it. You integrate, and you are done. And